Hello guys, welcome to this new video. So now we're going to go through question 10, the last question in the 2025 Specimen Paper 2. So here we're given this block oscillating with simple harmonic motion, amplitude A, and at t equals 0, it's at its maximum height. And then here we're given this graph that shows the variation of the height with time, and we need to state the equation of motion for this oscillation. Well, we can see that this is a cosine graph, so we need to write the equation of the cosine graph. We know in general that the equation of a cosine graph is of this form, so 2 pi over t, or well, bx, where b is 2 pi over t. So that's the coefficient of the x, and big A is obviously just the amplitude. Here we see we have a positive cosine graph as we have a positive displacement to begin with. So our height will just be our amplitude times cosine, and then 2 pi over t times small t. That is our variable, and that will be the equation of motion. And then we also need to sketch on these axes the variation of the velocity with time. And we need to label the peak value on the, so we need to label the peak velocity. And well, if we remember from simple harmonic motion, we always have a speed of 0 at the ends of the motion, and we have the maximum speed in the middle of our motion, always. So if we also see that at the start we're going to have a negative velocity as we're moving down, so we can assume that's negative as we are decreasing our height, then if we split this up into quarters of the period, as we will have to draw another trigonometric graph. So we're going, that's t over 2, this will be t over 4, and this will be 3 over 4t. We know at the start we have 0 speed as we're at the maximum height. Then after a quarter of the period we'll be at the middle, so that's going to be a maximum magnitude of velocity, but it's going to be negative as we're moving down. And then after half a period we'll be at the bottom of the oscillation, then we'll have a maximum speed again, and then 0 again. And then if we connect the dots, it should look like a negative cosine graph. And if we have learned derivatives from maths already, we could have also just seen that the derivative of a displacement time graph is the velocity time graph, and while the derivative of a cosine graph is negative sine. So from that we could have already come up with this graph, and now we just need to label this maximum velocity here. And well, if we look in our data booklet, the velocity of a oscillation can be given with this relationship, so x naught squared minus x squared, where this is our maximum displacement and this is the displacement at which we want to know our speed. So here we can also see that when this displacement is x0, then this whole thing will be 0 and we'll have a speed of 0. So when our displacement is equal to the maximum displacement, we'll have a speed of 0. But when this is 0, we have a maximum velocity. And well, that's what we want. So we want a maximum velocity. So we'll see that our V max is just equal to omega times x0. And well, we know omega is 2 pi over t, and our maximum displacement is amplitude. And we want to write it in terms of a and t. So this will be 2 pi over t times a. And then now we move on to a different part of the question. So now we're going to look at sea waves. And yeah, they're produced when wind carries energy, and it can be transferred into electrical energy. And this is a model of a wave where it has this wavelength lambda over 2. Or I mean, it has a wavelength of lambda, but this is lambda over 2. It has an amplitude of A and a width of W. And we need to show that the gravitational potential energy of the sea wave can be modeled with this equation, where rho is the density of seawater. Well, we know potential energy can be calculated with mgh. So somehow we need to use this equation. We just need to replace values with the correct aspects. So we know, well, first of all, let's look at the mass. We know that density is mass over volume. So mass is just density times volume. So we can say the mass of this crest is going to be this density times its volume. And well, the volume we can also calculate as we just have a cuboid with 3 sides given. We just have to multiply all 3 sides, and that will be the volume of our crest. So it will be density times lambda over 2 times A times W. And well, here we don't really have a point mass here. Usually when we calculate potential energies, we deal with point masses. And so it's obvious which height, like what height the point is at. But here we have like an equally distributed mass as there's water everywhere in this wave. But what we need to do in a situation like this is take the center of mass of the object, as that is where the gravitational force will be acting. So if we calculate the potential energy of this, we need to take the center of mass of this object. And well, if we look at what height it's at, it's going to be at the height of a over 2, as the entire height is a, and the center of mass should be in the middle. So that will be the height of our crest. So E potential will be mgh, and this is density times lambda over 2 times A times W times G times A over 2. And then we can combine the 1/2 to get a fourth, and then we'll have a density, we'll have a G, we'll have a W, we'll have a lambda, and we'll have an A squared. And so this is how we can show this relationship for the potential energy. And then we're also told that the wave is moving at a speed of v. The maximum power available from the c wave is p. We need to explain why the power per unit length is this expression. So we can see that the energy per unit length, so per unit length is just the energy divided by W. So what we'll have is the density G W lambda A squared divided by 4. So this is what we have had also here. And then we divide it by another W, as we just want it per unit length. So then the W's will just cancel out. And then the power we know is just energy per unit time. So power is energy over time. And well, this energy we calculated is already per unit length, so we just need to divide it by another time. So we'll have density G lambda A squared divided by 4t. And well, we know that lambda over t is a velocity. That's just the velocity of a wave. That's how we can calculate it. So then this can be simplified to 1 over 4 density G V A squared. This might be a little bit hard to notice, but if you get to this point, then you might want to look at what we're trying to achieve and see what similarities we have, and like, or maybe what's the difference, and then that can give you an idea of what to look for. Because if you look at this, you see that there's a V in here, and well, we didn't have a V yet, so you could try and think of how we could get a V in there, and well, then you might notice that lambda over t is just the velocity. And then this is not the total energy, not the total maximum power available, as this is only the potential energy. We also have kinetic energy, and if we remember the properties of potential energy and kinetic energy from simple harmonic oscillations, we might remember that they are in very close relationship with each other, because let's say that this is like the energy axis, and this is the displacement axis, so of a block or whatever, then our potential energy graph will look like this. So we'll have 0 potential energy when we're at the middle, and we have maximum at the edges of oscillation. And if we draw the kinetic energy graph, it's going to look something like this. It's not very symmetrical, but I hope you understand the point. So it's something like this. So we have maximum kinetic energy in the middle, as we discussed in this question, and we have zero kinetic energy on the edges. But what we notice is that they always add to the same value. So our total energy is constant. So we could say that the average potential energy and the average kinetic energy are the same throughout the oscillation. They're equal to each other. So we could draw in another line somewhere in the middle like this, for example, for the average potential energy. And this is analogous for power as well. So the powers are in a very similar relationship in this way. So we can say that the power from the potential energy and from the kinetic energy are equivalent. So power from E potential and E kinetic are equal. And so from this, we see that the total power will just be this times 2. Or we could do this plus another one of these, but that's just multiplying it by 2. So that's going to be 2 times 1 over 4 density GVA squared. So it'll be 1/2 density GVA squared. And this is what we had to show. And then we move again to another part of the syllabus. Now there's going to be a little bit about thermal energies and fission reactions. So here we have thermal energy being converted to electrical energy, and we have a fuel used to transfer this thermal energy at this pressure at a temperature of 550 degrees, and it condenses to a temperature of 30 degrees. And we need to explain, with reference to the second law of thermodynamics, why a steam turbine operating between these temperatures must be less than about 60% efficient. So what the second law of thermodynamics tells us is that the most efficient engine is the Carnot engine. So no heat engine can be more efficient than a Carnot engine. And while the efficiency of a Carnot engine can be calculated with the relationship that efficiency is equal to 1 minus Tc over Th. So the temperature of the cold reservoir, like where we are emitting the temperature to, the heat, and the temperature of the hot reservoir, so like where the hot temperature of the hot place we are getting the energy from, kind of. And well, it has to be in Kelvin, obviously. These usually always work in Kelvin, not in degrees. So if we convert 30 to Kelvin, that will be 303. And if we convert 550 to Kelvin, that will be 823. So this will be 0.63. So our theoretical max efficiency is 63%. And so this is approximately 60%. So we cannot have a steam turbine operating with an efficiency larger than approximately 60%, as then it would be a Carnot engine, but already the efficiency will be much, much lower. It will be around 30% because there will be many more losses. So usually it's very hard to get even close to a Carnot engine. And then now we have a fission. We get energy from uranium-235. And yeah, so fission is induced by colliding a neutron with this nucleus, and we'll have some common fragments that can be produced from this reaction. And we are told in a fission of two nuclei, two nuclei are produced with several neutrons. So this will be important. So this means that we get more than 0 neutrons. So we must be producing neutrons. And one of the products is 147 Ba. And we have to state a possible nuclear reaction. So we know our starting product is uranium-235. And we also know we have to collide it with a neutron. So this is kind of our reaction that is happening here. And we also know that beryllium is being formed. Ba. Like this. And we need to see what else could be formed. Well, we know that a neutron, well, we know that both sides of a reaction must have the same proton number and the same mass number. So we need to add something else to this, but we also know we'll have to add some neutrons. But no matter how many neutrons we add, we don't increase our proton number. So we need to choose an element that if we add 56 to, we'll get 92. And well, if we look, that must be 36. Because 36 plus 56 is 92. So that will be Kr 56. And then we see we have multiple options of what we could choose from. If we choose 88 or 89, that would be too much, as if we add that to 47, then we have no more space anymore to add this one from the neutron. So for example, we could add 87, and then if we do 147 plus 87, we still need neutrons, as this is only, well, this is not enough yet, because here we have 236, here we're only going to have 234, so we still need 2 neutrons to balance the reaction. We could have also added an 86 here, but then we would need 3 neutrons, but both are fine. What we could not have done is chosen another one such that we have no neutrons being produced, as we are told that neutrons are being produced. And then we are told that how much energy we get from one fission reaction. And we're also given the energy density of coal. We need to estimate this ratio of energy density of uranium to energy density of coal. So energy density is energy per unit mass. So this is already in correct units. Somehow we need to convert this mega electron volts to the units of energy density. So convert 200 mega electron volts to joules. So we can convert that pretty simply. We need to first convert to electron volts. So that's 200 times 10 to the 6. And well, we need to still multiply by 1.6 times 10 to the minus 19, so that we convert it into joules. And we also want to convert this not only to joules, but we want it to be joules per kilogram. And we know that this is how much energy is released by one atom of uranium-235. But we want, if we can calculate how much energy is released per mole, or if we use fission to react 1 mole of uranium-235, then if we see how much energy we get from that, then we can use the fact that the molar mass is 235 gram per mole, and then we can convert it into kilograms. So if we still multiply this joules by 6.02 times 10 to the 23, we'll get the energy we get from 1 mole. So this will be 1.9 times 10 to the 13 joules by 1 mole of uranium-235. In the mark scheme, by the way, I believe there's a minus sign in front of the 23. Don't ask me why, that must be a typo, as if you plug in minus 23, the answer that comes out is incorrect. So yeah, and this is Avogadro's number anyways, so yeah. And then we know that 1 mole is equal to 0.235 kilograms. As we know, 1 mole is 235 grams. So we want joules per kilogram, as that is the units of energy density. So that will just be 1.9 times 10 to the 13 divided by 0.235. So that will be 81 times 10 to the 12 joules. And then we just need to compare these ratios. So we need to divide these two numbers we found. So 81 times 10 to the 12 divided by 25 times 10 to the 6. This will be 3.2 times 10 to the 6. So we see that the energy density of uranium is much, much, much larger than of coal. So by burning 1 kilogram of both, we get a lot more energy from uranium. And then we are also told that energy in a star arises from nuclear fusion. We need to identify one advantage and one difficulty for this to become a reality. So one advantage is that we have no radioactive waste. So that's definitely a positive. We also have no greenhouse gases being produced by the reaction itself. But a difficulty is that we need very high temperatures, which at the moment are not yet really possible to achieve in a reasonable manner. Very high temperature needed. We're still at the point where the energy needed to produce such an environment requires more energy than what the reaction itself gives us. So if we would use this, then we would technically be losing energy. So it's not very efficient. And this last question is a little bit interesting. This is I think a little bit of a new style question in IB physics. This is more of like a discussing question where we could write quite a lot. We need to discuss the efficiency of these different methods with respect to these qualities. So I don't want to write a whole essay for you guys, so I think I'm just going to mention some main points, and then from this you could craft your own answer, I think. So let's see first of all the efficiency of these methods. So the least efficient will be sea waves. Tidal power is usually the least efficient. Then coal and fission are very similar. And then fusion has the potential to be the most efficient if we could achieve this, but as I said, this is not really yet possible. And well, you can also see from our question that the energy density of fission is much larger than of coal. So that's what we calculated up here. So we could also mention this in our answer. And then we can also look at the environmental impact. Total impact of all of these. So we had we had coal, we had fission, we had fusion. Well, sea waves have very minimal environmental impact. Coal has high CO2 emissions and greenhouse gases in general. Fission has low emissions of greenhouse gases, but we produce radioactive waste, so that's not very good. Radioactive waste. And then fusion again forms very minimal waste, no real radioactive waste or greenhouse gases, so that's very nice. And then we can also talk about the availability of these. Again, we had sea, coal, fission, fusion, like this. Well, sea is location dependent. So obviously if in a place there is no sea or large bodies of water, we cannot really use this. So it's kind of limited as to where we can apply this form of energy or this method, but it's renewable. So that's nice. And then coal is quite abundant at the moment, but it will run out. So it's not renewable. And then fission is kind of in a similar situation as coal. So it's abundant, but not renewable. The uranium we're using is quite abundant. And then fusion is technically limitless. as we would just be using isotopes of helium like deuterium, tritium, and these are like unlimitedly available almost. So but the method itself is not yet possible to achieve, so we're not really ahead of that. So you could come up with some combination of these arguments to discuss these methods. And well, yeah, obviously make sure that you stay within the bounds of the question, as if you would write underneath like I did over here, then your examiner would not mark that part anymore, as they don't get to see it. If you want to write more, then you need to request for an extra piece of paper and then continue your explanation over there. And well, this was the end of the 2025 Specimen Paper 2. I hope this was all helpful, and see you in the next videos.